In addition to point estimation, we can also construct a confidence interval. If we pick up a different sample, we will get a different sample mean each time. Virtually, the sample mean would never actually equal the true population mean, as you can see from the right-hand side. Each sample, the sample mean is not necessarily the same as the population mean. Instead, we want to construct an interval that captures the population mean with high probability. Distributional values taken by a statistic, the mean in this case, in all possible samples of size n from the same population, is shown in this graph. We do have an assumption. Our observations at x sub I are sampled from a population with mean of mu and variance of sigma squared. The confidence interval. A 100 times 1 minus alpha % confidence interval for a parameter has two parts. An interval calculated from the data, usually in the form of estimate plus minus the margin of error. The margin of error is equal to the measure of how confident we want to be times the standard error of the statistic. The second part is a confidence interval level, 100 times 1 minus alpha, which gives the probability that the interval will capture the true parameter in repeated samples. For each sample, a confidence interval can be constructed. For example, a 95% confidence interval means that if you take 100 random samples, then 95 intervals will capture the true population mean. It is wrong to say that there is a 95% of the chance that the population mean will lie within the interval. The sampling distribution is needed to calculate the margin of error. A 100 times 1 minus alpha confidence interval for the mean mu in a normal distribution with known sigma is given by y bar plus minus z alpha over 2 times sigma over square root of n. Because we know in this case the population is normally distributed and we know its standard deviation, therefore the sampling distribution follows a normal distribution. And in this case, we also know the standard error of the sampling mean is sigma over square root of n. And z alpha over 2 is an up-tailed percentile of the standard normal distribution, as you can see from this graph. When population standard deviation sigma is unknown, sigma is estimated by the sample standard deviation S, and a 100 times 1 minus alpha % confidence interval is represented by y bar plus minus t sub n minus 1 alpha over 2 times s over square root of n. In this case, the sampling distribution is a t distribution instead of the z distribution in the previous slide. A t distribution is determined by a single parameter nu called its degree of freedom. When nu approaches infinity, t distribution becomes the standard normal distribution. Now, it's important to notice, although there is only one z distribution, there are many different t distributions, as you can see from this graph. The way we distinguish those t distributions is to use the degree of freedoms. Heuristically, the number of degrees of freedom means the number of independent values used for calculating a sum of squares. The number of independent pieces of information that go into the estimate of a parameter is called the degrees of freedom. In general, the degrees of freedom of an estimate of a parameter is equal to the number of independent scores that go into the estimate minus the number of parameters used as intermediate steps in the estimation of the parameter itself. For example, if you are calculating for sample variance, the sample mean will be the only intermediate step. So the degree of freedom when you calculate it for sample variance will be n-1 because sample mean is the only intermediate step. As a rule of thumb, every estimate of a population value in a formula equals 1 degree of freedom. For example, when we calculate the sample variance s squared, we have n-1 degrees freedom. Although we started with n independent values, y sub I, 1 degree of freedom is used to calculate the sample mean. Therefore, the degree of freedom when you calculate the sample variance will be n-1 degrees of freedom. Hypothesis testing. In statistics, a hypothesis is an assumption or theory about the characteristics of one or more variables in one or more populations. Typically, you have a theory, you want to make a statement about some characteristics of a or more variable in one or more populations. It can be formulated in terms of population parameters. It's important to notice that the hypotheses are about population parameters. It's wrong to list sample statistics in your hypothesis. The null hypothesis H null is the statement being tested. It usually contains the words such as no effect or no difference. Mathematically, the equal sign should go here. The alternative hypothesis HA is usually the claim we're trying to find evidence for. A lot of times you have a theory, you have a hypothesis. The alternative hypothesis is what you wanted to prove. It usually contains the words such as not equal, greater than, or smaller than. When you see not equal, we're talking about a two-sided test. Greater than or smaller than gives you a one-sided test. P-value is a very important concept. P-value stands for probability value. The p-value is the probability computed assuming that H null is true, that the test statistic would take a value as extreme or more extreme in the direction of HA than that actually observed. It is a way assessing the believability of H null given the evidence provided by a random sample. If p-value is 0.02, it means that there's 2% chance that the test statistic would take a value as extreme or more extreme in the direction of HA, assuming H null is correct. Therefore, it is very unlikely you would reject H null when p-value is small. Could random sample variation alone account for the difference between H null and observations from a random sample? Here we use p-value to help us to understand that a small p-value implies that random variation, because of the sampling process alone, very unlikely accounts for the observed difference. Therefore, when p-value is small, we reject H null. It means the true probability of the population is significantly different from what was stated in the H null. In fact, the significance level alpha is the largest p-value tolerated for rejecting a true H null. This value is decided arbitrarily before conducting the test, although it is widely accepted or used using alpha of 0.05. To help us to remember the decision, you can remember this. When the p-value is low, the null hypothesis gotta go. In a one-sample t-test, to test the hypothesis, null hypothesis mu is equal to a value based on a small random sample of size n from a normally distributed population. The sampling distribution is a t-distribution. The t-test statistic can be computed by using y bar minus mu sub 0 over s over square root of n. And this t-distribution has a degree of freedom of n minus 1. And here we provide a two-sided test, one-sided tests, and you can see how you can calculate the p-value associated with each situation. An equivalent way for testing a hypothesis is to use critical values for a given significance level. When the test statistic t sub 0 falls within the rejection region, now a rejection region is represented by the red area on the tail side. The p-value is smaller than alpha and we reject H0. The boundary of the rejection region is specified by critical values. To test the hypothesis mu is equal to mu0 based on a small random sample of size little n from a normal population with unknown mu and sigma, we need to use a t-test statistic. We will reject H0 at significance level alpha against a one-sided alternative if t sub 0 is greater than or equal to t sub n minus 1 alpha for a upper tail test,